see source coding theorems. In previous lecture, we have seen block diagram of digital communication system. So in transmitter section, in that block diagram, we are using source encoder at the input side. So we know the function of source encoder. Whatever input signal we have for the transmission, that is in digital form, so we are converting that signal, or we can say we are encoding that signal into one new bit sequence using the source encoder block. So source encoding is used to represent the data generated by discrete source efficiently, and device used to perform this function is we call that device as a source encoders. So here is one diagram shown in which we have considered the DMS, that is discrete memory source DMS, which generates your information signal in discrete form, and when that information is passed through the source encoder, that source encoder generates new binary sequence. We can say that that source encoder encodes your information in another form, another digital form. So output of this DMS is converted by source encoder into a binary signal. We call that signal as a code word. At the output of encoder, we are getting that code word. So that signal is used for the transmission. So there are different source encoding techniques we are going to study in this lecture. Before that, we will see some terminology related to this source encoding topic. So first definition we are going to see here is average code word length. Now code word, we know what is code word. Code word is the coded sequence generated at the output of source encoder. So what is now average code word length is, so code word length L represents the average number of bits per symbol used by source encoder in process of source encoding. So number of bits generated per symbol by the source encoder represents our average code word length. It is denoted by capital L, and this code word length is given by L equals to this formula summation pk into lk, where k goes from n to m. This lk represent the length of messages in mk bits. Okay, so the formula we have for average code word length L equals to summation pk lk, where k goes from 1 to m, where m are the number of messages and p is related to the probability of occurrence of those m messages. Now the next definition we will see here, coding efficiency. So now what is coding efficiency means. So coding efficiency represents how effectively a source encoder uh, generates a code sequence or code word. So suppose Lmin denotes the minimum possible value of capital L, which is the code word length. So coding efficiency is given by eta equals to Lmin upon L. Lmin is the minimum length of the code word generated by that source encoder, and L represent the length of that code word. So ideally value of this coding efficiency should be equals to 1 or 100%, and practically it should be as high as possible. So a source encoder is said to be efficient if the value of coding efficiency is close to unity. Okay, so source encoder we can say is more efficient when the value of coding efficiency is equals to 1 or close to unity, or we can say 100%. Ideally it should be that value, and practically it should be as high as possible. So these are the two terms, that is one is length of code word and the coding efficiency. One more point is there, that is called as a code redundancy. So redundancy is what? Redundancy is actually we are using source encoding method to reduce the effect of redundancy. Redundancy is unwanted bits occur in code word generated by the source encoder. So this redundancy should be as low as possible. It is opposite to coding efficiency. So redundancy is given by gamma equals to 1 minus coding efficiency. So these are the three terms we will be needed to solve numerical on this topic. So we will see first source coding theorem. So first source coding theorem statement is, suppose we have given a discrete memory source with the entropy h and average code word length l. So for any source coding, the source coding theorem states that it is bounded as l greater than or equals to h. Now what is l? L is our code word length and h is the value of entropy or average information. So this first source coding theorem states that the average code word length should be always greater than or equal to source entropy h. That means if here we can say the minimum value of the code word uh, length, that means capital L mean equals to h. The minimum value of code word generated should be equals to h, and the maximum or it can be greater, it should be greater, actually it should be greater than the average value of information or entropy. So minimum should be L min, minimum value of length should be equals to h, and the code word length should be greater than h. Maximum value should be greater than h. So if we substitute this value in the equation of efficiency, coding efficiency eta, so the equation previously we have for coding efficiency L mean upon L. So if we put here a minimum value of L mean as h, so we will get equation for efficiency in terms of entropy and the code word length L as h by L. Now we will see different methods of source coding technique. So first method we have in syllabus, that is Shannon-Fano code method. So we will see that coding method first. So first method of source coding is Shannon-Fano code method. So in this method, suppose we have given a discrete memoryless source generates m messages which are equally likely. Means all the messages generated by the source are equiprobable or they have same probability of occurrence, that means equally likely message. Then we know the equation for entropy. We have seen this equation in previous lecture. The maximum value of entropy when all the messages are equiprobable, the value is given by equation capital H equals to log to the base 2 capital M. Okay, so if each message is coded in n bit sequence, suppose we have capital N number of messages and each message is coded into capital N bit word, so the number of bits per messages is given by 2 raised to capital N. So total bits per this message is capital M equals to, we can write M equals to 2 raised to n bits per messages. Okay, so if you put that value in equation of entropy, we will get equation of entropy as H equals to log to the base 2 raised to capital N, which is equals to, after simplification we can write as capital N bits per message. And if you put that value of entropy in equation of coding efficiency, which we have already, h by L, so if you put value of h equals to capital N here, and the length is again n bit given. Okay, total length of the code word is capital N now, because message is coded into n bit word. So we will get equation of coding efficiency as capital N upon n, which is equal to 1 bit. That is the maximum value of coding efficiency required. This is the case when all the messages are equiprobable. But if messages are not equally likely, then what happen? This relation between the entropy value capital H and N is given by this equation. The entropy value is less than the total number of bits produced by the source, or we can write this as H by N is less than 1. Okay, so this carries less information, and which should not happen. So how we can solve this problem? So Shannon Fano source coding method is used to solve this problem. So we will see how we can simplify or produce a effective code word using Shannon Fano code method when the messages are not equiprobable. So there are some steps or algorithm in Shannon-Fano code technique. So we will see those methods or steps in this Shannon-Fano code method, how we can produce a code word with efficient code length when the messages are not equiprobable. So for that we just have to follow these steps. So steps given in Shannon Fano code method. The first step is list all the messages in order of decreasing probability. See now here, when the messages are not equiprobable, the value of probability of each message will be different. Probability of occurrence for each messages will be different. So in that case what we have to do, we have to list all the messages in order of decreasing probability. Then second step we have to do in this Shannon Fano code method, that is partition the set of symbols into two sets that are close or possible to being equiprobable. Means we have to partition the given messages into two sets which has a same probability or nearly equal probability. Now assign 0 to each messages in upper set and 1 to each message in lower set. So whatever two sets we are getting, so whatever message we have in that each set, so we have to assign 0 to all the messages in upper set and 1 to all the messages in lower set. Now next step, we have to continue this process each time, partitioning the set with as nearly as equal probability as possible until it is not possible to further partition the messages. Okay, so these are the four steps involved to generate the Shannon Fano code. We will see this method with the help of numerical, so it will be easy to understand. Suppose in numerical we have given this messages. Total 8 messages are given with a different probability value. For M1 it is 1 by 2, for M2 1 by 8, M3 1 by 8, M4 M5 M6. All three messages has probability 1 by 16, and M7 M8 given with the probability 1 by 32. Now all these messages are having different probability. So how we can generate a code word using Shannon Fano code method for these different probability value messages. So here just follow the steps given in Shannon Fano code algorithm. So we have to first arrange all the messages into decreasing order of probability. So here we have arranged all the messages. Say first two columns, the messages are already given in decreasing order of probability. So what we have to do, just we have prepared two columns, one for messages and one their probability. Okay, so what next thing we have to do, we have to partition all the given messages into two sets such that the probability of these two set will be equal or nearly equal. So how we can partition these messages given with the equiprobable set? So let's see how we can partition. So probability of first message is 1 by 2, then probability of this message next M2 M3 is 1 by 8, M4 M5 M6 given 1 by 16, for M7 M8 probability given is 132. So how we can divide now this messages into equiprobable set? So see, from the bottom we will start with the least probability message. See, the 1 by 2 is the highest probability given in this numerical. So we will start with the lowest probability. If we add the last two probabilities of M7 and M8, 1 by 32, 1 by 32, which will give you value 1 by 16. If you add that value, if you add that value with this 1 by 16, we will get that probability as 1 by 8. Again, probability of addition of these two will be 1 by 8. So if we add that this 1 by 8 and this 1 by 8, I'll get 1 by 8 1 by 8 as 1 by 4, and again for this addition I'll get equation 1 by 4. So 1 by 4 plus 1 by 4, the probability, total probability of addition of all these messages from M2 onwards till M8 will be 1 by 2, and the probability of M1 is already given as 1 by 2. So we have here two sets in which In first set, in upper set we have message M1 with probability M2, and in lower set we have all these messages from M2 to M8 with the probability, total probability, addition of all this probability, we are getting the value as 1 by 2. So we can divide this messages given into two sets with the probability, with the equal probability as 1 by 2. So we have to partition these messages into two sets according to these sets. Okay, so in upper half, so we have two sets. In first upper set we have only one message, that is M1 with probability 1 by 2, and in lower set we have these messages M2 to M8 with the with this addition of all the probability, that is 1 by 2. So next step in this Shannon-Fano code method is we have to assign 0 and 1. So to the upper set we have to assign 0, whatever messages we have in upper set, assign 0 to all those messages. We have only one message in upper set, so assign 0 to that message, and in lower set whatever messages we have, so all message to all message we can assign 1 here in lower set. So in lower set we have assigned 1 to all the messages. Okay, see the red line indicates the partition between two set. So in upper set we have only 0, and in lower set we have all these messages with a 1 value. Okay, now in second column, that is the next step. So in second step what we have to do, we have to continue this process till the messages or set cannot be partitioned. So see here, first for M1 we cannot partition that set because we have only have one message in that set. So for M1 we have to stop here in second column. Now for the next set, okay, from M2 onwards we have to partition, we have to do partitioning. So how we can partition again with the equiprobable set? So see here, if we add the two messages M2 and M3, the probability value will be 1 by 4, and if we add the 4 messages in lower set, that is 5 messages we have from M4, M5, M6, M7 to M8, if we add probability of all those messages, the value will be 1 by 4. So we have here two sets with the probability value as a 1 by 4. So we can partition this set, okay, into two sets, two subset with M2 and M3 in one set, and M4, M5, M6, M7, M8 messages in another set. So assign now again 0 to upper set, all the 0 to all the messages in upper set, and 1 to all the messages in lower set. Again here, see now for upper set we have two messages. So again we can divide those two messages with the equiprobability as 1 by 8, 1 by 8. So assign, so I have divided here this M2 and M3 again into 0 and 1. Okay, that is subset we can say. And for lower set again we can do partitioning with the same method. Okay, divide that messages given with into two set with nearly equal probability or equal probability. So likewise you have to continue those steps till nothing is left for partitioning. So we are getting these 5 columns, okay, with the different values of 1 and 0 in each column. So from this column now we can write code word. So to write code word here for first message M1, just check the columns. We only have this 0. Okay, so for to write code word for this M1 message, write the 0 as it is here. So code word for M1 will be only this 0. Now to write code word for M2, just check this columns. We have here 1 in first column, 0 in second column, and again 0 in third column. So write those bits as it is. So that is the code word for M2. Similarly, code word for M3 we can write 101. For M4 we can write all the bits present in this 4 column. Okay, so likewise we can write code word for all the messages. Okay, so I am getting these code word values, okay, or number of bits present in a code word. So I can find the code word length for each message. So code word length for each message, code word length represents the number of bits present in that code word. So for M1 the code word length is 1. For M2 the number of bits in code word for M2 3, so code word length will be 3. For M3 3, M4, M5, M6 code word length is 4, and M7 A M8 code word length is 5. Okay, once I get this value of code word length, I can find the value of capital L. So for to calculate capital L, I have equation summation of pklk, where k goes from 1 to capital M. So total we have 8 messages. Value of M is given as 8. So put that value of probability of occurrence for all the messages, and the value of code word length which we have obtained here using Shannon Fano code. So after solving this, I'll get value of L as 2.315 bit per message. Again, to calculate coding efficiency, we need value of entropy. So we know equation for entropy in terms of probability as pk log to the base 2 1 by pk, where k goes from 1 to m. If you solve this, you will get the equation for you will get value of entropy as 2.32 3125 bits per message. So coding efficiency will be ratio of this entropy and code word length capital L into 100%. So the coding efficiency value is 1 or 100, we can say that is the maximum value actually we are getting, because here entropy and the code word length values are same. So I am getting coding efficiency eta equals to 1 or 100%. So redundancy in this case here 1 minus coding efficiency, that is 1, 1 minus 1 0. So redundancy here is 0, which is low value I am getting for redundancy. So that's how a code word length and a coding efficiency can be we can find out using this Shannon Fano code method. Okay, so we will stop here. So that is all about Shannon Fano code